In the last lecture, we had introduced uh, the basic idea of propositional logic, and we talked about the representation of different sentences in propositional logic. In this lecture, we will look at the formally how do we make inferences when some statements are represented in the form of propositional logic. As it has been told in the last lecture that the objective of a knowledge representation scheme is not only representing the facts or some rules, but also we have to be able to make the inferences. Unless we can make inferences, the knowledge that we have in whatever form we represent that will be of no use. So, we will be talking about inferencing in propositional logic representation today, but before we proceed with that, let us have a quick look at some of the answers to the quizzes that were given in the last lecture. Now, instead of going into all the problems that were given, I will rather give you some examples. Like the first problem was, it rains in July. Now, how do we represent this in propositional logic? This is really a simple case. We can say that rains July. That is sufficient to say that it rains in July. Similarly, if the statement was that it does not rain in November, in that case we could have written it as not rains November, etc. Okay. So, this is rather simple, but the next example that we have, this was also one of the problems given. If it rains today and one does not carry umbrella, he will be drenched. Now, this one how do we represent? As you can see, there is some implication here, if and then. Okay. If it rains today and one does not carry umbrella, then he will be drenched. This then is implicit here. So, we can say rains today for this part of the clause, rains today and does not carry and not carry umbrella. If these two things happen, then get drenched. Okay, this is one way, but here I have done some mischief, I would say. Here you see that there is a word one, and one I have somehow escaped that one does not carry umbrella. I have simplified that because in order to capture this sort of thing, one does not carry umbrella, no one carries umbrella, somebody does not carry umbrella. This sort of constructs require some more power than what is provided in the case of propositional logic. So, let us neglect or ignore this one part here for the time being. So, if we neglect that, we will get rains today and carry umbrella and does not carry umbrella implies that somebody gets drenched. Now, if we make it, if we do away with this problem of 1 here, then let us take another example. Rains today and Tom does not carry umbrella, that implies that Tom will get drenched. So, rains today and not carry umbrella Tom, get drenched Tom. In this way, you can try the rest of the examples. I think there were 2 more there, which you can try and you can get them across, I think. The only tricky thing was here. So, now let us come back to today's lecture. In today's lecture, our objective is to put you in a position where you will be able to infer the truth values of a proposition. You know that any proposition can be true or false. The truth value of the proposition will be evaluated. How to evaluate that? And reason, you will be able to do reasoning towards arriving at new facts when you are given a new set of propositions. Also, this will help you, this lecture will help you to prove a proposition given a set of propositions. That means, when a set of propositions are given and another proposition is given, then you have to prove this later proposition using the existing propositions which are known to be true. Now, what is the mechanism of doing that? We will see that too in the lecture today. So, coming to the next one, I had given 2 parts of the quizzes, one I have answered, the other one I have not, but I assume that you have been able to do that uh, in some way or other, but since we did not introduce any formal method for doing it, I will try to give the answers of those a little later. But before that, let us look at the procedure that is formally adopted to arrive at the truth value of compound propositions. So, suppose we have got a proposition P and proposition Q. The objective is to arrive at the truth value of the composite propositions like P and Q, P or Q, etc. Now, the standard method for doing that is using the truth table. Now, here you see that we are deriving a truth table for the AND logical operation. So, P and Q, each of them P or Q can have a value true or false, right. Now, so we can have 4 combinations, both of them are false, one is false, one is true, one is true, one is false, and both of them are true. So, we make a truth table like this. There is a slight small thing to be noted here. We usually try to follow a system while we enumerate them: false, false, then we make one of them true, false, true, then we make the other one true, the other one false, true, false, and then true, true. So, this is a typical order in which we usually write. So, let us see, when we talk of P and Q, you know that AND is true if both of them are true, if both of the propositions are true. So, when this false, false, P and Q will be false. If P is false and Q is true, then P and Q will be false, because it requires both of them to be true. True and false will become false. Only when both of them are true, it will become true. Similarly, if we go over here now, we can see, follow the mouse pointer, again the same combination is there, but OR operation P or Q will be true when any one of them, either P or Q, any one of them is true. So, you see false, false will be false, but in false true case, when since one of them is true, the result will be true. True or false, one of them is true, so it will be true. If both of them are true, then also it will be true. That is how we can find out the truth value of this composite propositions P or Q. Let us have a few more examples. Here we are looking at the implication logical operation. Now, what does implication mean? It was told in the last lecture. If P is true, then Q will certainly be true. So, P is a sufficient conditions for Q's being true, but if P is false, then also Q can be true, all right. And if P being false, still Q is true, then also P implies Q, this statement is not violated, all right. So, the truth table will be both of them are false, then obviously this is true, because it is telling the truth that if it is false, it may be false, that is true, this entire thing is true. If this is false, if P is false here and still Q is true, yes, that can happen, because P is a sufficient condition, P is truth is a sufficient condition, but not a necessary condition for Q's being true. So, you see, if it is false and Q is true, P implies Q, this statement, is this statement true? Yes, it is still true. Now, if P is true and Q is false, now we have a problem, because P is a sufficient condition. So, if P is true, Q has to be true if this is true, but P is true, but still Q is false, then obviously P implies Q, this statement does not hold. Therefore, P implies Q becomes false. But if both of them are true, then also it is true. So, when we try to derive the formula for one such composite or say composite statement in propositional calculus, we can use this method called truth table. Now, here we have taken the example of a little more complicated thing, that we want to find out the truth value of the statement not P or Q implies P and Q. Now, when will this statement be true? Is it true? Let us see. Now, again we start with the standard method of enumerating the truth values of P and Q. Now, we will have again these 4 combinations: false, 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 true, true, false, true, true. Now, again, since we have got not P here, so if P is false, then not P is true. We make a column for not P. P is false, not P is true. P is true, not P is false. P is true and not P is false. And now, we make another column for this entire thing, not P or Q, and that column is here, not P or Q. And so, not P or Q, how do you compute? It is an OR. So, not P is true, Q is false. So, not P or Q is true, not P is true. Look, now I am just looking at these 2 columns because I need only these 2. Both of them are false, this will be false. This is false, this one is true. So, this will be true. So, I have got the truth value of this, and on this side we have got P and Q, all right. Now, we have got P here, Q here. So, P true, P false, Q false makes it false, P false, Q true makes it false, and only when both of, since it is AND, when both of them are true, it becomes true. Now, I have got these 2. Now, I want to see whether this statement, which is an implication between this implies this implies this, whether that is true. Now, what is the truth scenario for that? If the antecedent is true, if this part is true, then this has to be true, because this is a sufficient condition. Now, we see here this is true, but this is false. So, this combination makes this entire statement false. Similarly, I have done some mistake here. This should be false, this should be false, and this should be true. There is a mistake here, I am sorry. This should be false and this should be true, then this should be true. Okay. This so, if this is false and this is true, then this should be true. If both of them are false, then also this is true. If both of them are true, then this is true. Okay. So, now we come to another very important theorem, that is called De Morgan's theorem. De Morgan's theorem states that if I make a negation, say for example, P and Q is negated, P and Q is, this entire thing is negated, then each of these literals, each of these propositions like P and Q will be individually negated, and this operation will be complemented, its dual one will be taken. So, the dual of AND is OR and the dual of OR is AND. So, not of whole thing P and Q will be not P, and this one will be complemented, it will become OR not Q. Similarly, not of P or Q will be not P, and this will be complemented and not Q. Now, this is De Morgan's theorem. So, if we just write down that to prove this, the truth table, then we can see that P and Q will have these combinations again. So, P or Q will have this value, not of P or Q will be complement, right, true, false, true becomes false, true becomes false. Now, we look at the right hand side of this side, not P, here P was false and not P is true, Q was false, so not Q is true. So, we get not P and not Q, these things, and so not P and not Q, true, true will become true. So, I am trying to compute this part, I am trying to prove De Morgan's theorem. So, I have found the truth column for this value, now I am trying for this value. So, as soon as this becomes true, false, 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 I can compare this column and this column, I can see they are identical, right. Therefore, these two are equal. So, that proves De Morgan's theorem. The next thing that we can now do is retry the earlier quiz. What was given here is, if P is true and Q is true, then are the following true or false? First thing that was given was P implies Q. Is it true or false if P is true and Q is true? Now, we have got a formal method at our disposal. So, let us make a truth table for that. We see that P and Q, and P implies Q, if we make this truth table, we will find that if P is true and Q is true, P implies Q is true, right. Now, let us take the second example. The another example was, therefore, I am just showing the results of 2. Not P or Q implies P. How do we deal with that? Again, if P and Q are true, is it true? Let us see. Say here I have used another notation, not P can be written in this, or P prime can also be used to denote not P. So here you have see P, here you see P is true, because it has been told in the problem if P is true, then P prime is false, okay, negation of P is false, and Q is true. Then what happens? S is this entire statement. Is it true? Let us see what happens. Not P is false, so this is false, Q is true, and therefore this part is true. All right. This part is true implies that P and P is also true. So this is true implies that this is true. So this entire statement is true. Okay. So you can therefore use the truth table method to derive the validity of correctness of any propositional statement. Now let us come to reasoning. How do we carry out reasoning in the case of propositional logic? So what do we mean by reasoning? That you are given some propositions, you are given using the given propositions which are assumed to be true, you are trying to derive new facts which will also be true. Okay. So suppose there is a proposition, it is the month of July, okay, and there is another proposition, it rains. Okay. Now, and there is a rule that is told that P implies Q, that means if it is the month of July, then it rains. This is the statement. Now another statement is given, it is the month of July. That means P is told. Then what can you infer? Using your common sense, you can say that you can conclude that it rains, right? Now how do we do it? What was the mechanism that went behind this? We can write this in this form. Say P implies Q, this is a true proposition. If it is the month of July, then it rains. And it is also told it is the month of July. Then so if P implies Q and P, then we can infer Q. So P implies Q is given and P is given. So we can infer Q. This is a very common deduction technique that we often use in our day-to-day life, and it has got one name, and that name is modus ponens. Modus ponens. Okay. This is one typical inference rule which is very popularly used for carrying out inferences. All right. Now, why is it true? You see, P implies Q can be, is modus ponens a valid, is it a correct inference rule? Let us look at that. P implies Q can certainly be written as not P or Q, that we have seen in the last class. Not P or Q, they result in the same truth table. So we have got not P or Q and P is true. So if we conjoin it with P, then we can write P and not P or Q, and therefore P and not P by associativity or Q. So P and not P is false or Q, anything false or Q will be Q. So that is the proof of the modus ponens. That means if P is given and not P or and P implies Q is given, then we can certainly infer Q, and that is a very common and useful inference rule. And when we talk of a valid inference rule, it is irrespective of the interpretation. We are talking of inference rules which can be mechanically applied, and these are irrespective of the meaning, that is the interpretation that we give. So modus ponens allows us, irrespective of whatever the interpretation is, to infer the truth of Q. So modus ponens is an inference rule that allows us to deduce the truth of a consequent depending on the truth of the antecedents. It is just a rule. Okay. Now, why are we so much bothered about inference rules? We are so much bothered about inference rules because we want to develop some mechanical procedure using which we can make the machine infer new facts. So we must, only those inference rules are of interest to us which can be mechanically applied. Besides modus ponens, there are a couple of other inference rules, like which you can see through your common sense. If P and Q, if P is true and Q is true, then obviously P is true. Okay? If P is true, then P or Q is true. All right? If not of P is true, then P is true. It is a double negation, and by De Morgan's law or whatever, it is a double negation. So, these two will cancel out each other and then we will get P. Then there is a very interesting and useful rule that is called the chain rule. For example, if we have one rule like if P is true, then Q is true, and I have got another rule, if Q is true, then R is true, then we can certainly infer that if P is true, then R is true, because P is being true makes Q true and Q is being true makes R true. So, there is a chaining. P is true makes Q true and Q true makes R true. So, therefore, by transitivity we can say if P is true, then R is true. This is called a chain rule, which will find a lot of applications when we look at rule based systems. So, now we come to a very, besides these inference tools, now we come to a very important concept called satisfiability. Satisfiability, what does it mean? Let us remember that whenever we try to prove any proposition, we are proving it with respect to a particular interpretation, and that interpretation is nothing but mapping to a world. And a sentence is satisfiable by an interpretation if that interpretation makes the sentence true. That means, if under that interpretation that sentence evaluates to true, only then that interpretation satisfies the sentence. Okay? Now, if no interpretation makes a sentence true, there is no interpretation that makes a sentence true, then that sentence is called unsatisfiable or inconsistent, unsatisfiable. If there are no interpretation that makes all the sentences that you have in a set true, then that set of sentences is inconsistent, okay, or unsatisfiable. So, this is a very important notion, satisfiability. So, briefly speaking, what does it mean? It means that if given an interpretation, a sentence evaluates to true, then that interpretation satisfies the sentence. The sentence is satisfied under that interpretation. Now, this leads to a very important concept called logical entailment. We often in our day-to-day use, way of speaking, we often say this is a logical consequence of that, this logically follows from that. Now, what does it mean really? It logically follows? What does it mean by following logically? That is essentially captured in the idea of entailment. If something logically entails something else, then we can say it is a logical consequence. But what I said now is equally vague. So, let us try to make it concrete. Suppose there is a set of sentences S, suppose, and let us suppose there is another sentence, small sentence here, small green bubble, that is another sentence, and we are thinking of one particular interpretation I, one particular interpretation that have been given to this set of sentences, and this interpretation obviously makes these set of sentences true. That means, this interpretation I satisfies this set of sentences, okay, satisfies this set of sentences. Now, suppose we apply the same interpretation to this new candidate sentence, and if the same interpretation also makes this sentence true, that means, the interpretation that made these set of sentences true also makes this candidate sentence true, then we can say that these set of sentences logically entail this sentence. Okay. These set of sentences, when true, will also make this one true. Okay. So, that is called logical entailment. Now, if put in words, if a sentence S1, that was our small bubble here, that was our small bubble here, suppose this is S1 and there is a set of sentences, okay, capital S. if a sentence S1, there is a small bubble, has a value true for all interpretations that make all sentences in a set of sentences S true, then we can say that this set of sentences S logically entails S1. That means S set of sentences logically entails this new sentence, or in other words S1 logically follows from S, or S1 is a logical consequence of S, etc. So, now we no longer remain to be vague about when we say that this thing logically follows from this thing. That means, a particular interpretation, when it makes a set of sentences S true, will also make the new candidate sentence S to be true, small s or S1 to be true. All right. Now, this is a very important consequence of our understanding of logical inference, because when we try to infer, we are actually trying to derive new sentences which are correct, which are valid. Now, just looking at again in another direction from the angle of inferencing. Suppose we have got a set of sentences here, and I have got a new proposition or a new sentence also here, and I have got a decision machine. The decision machine takes this set of sentences which are known to be true. Suppose I have told some geometry theorems to our machine. Now, these geometry theorems are already proved and they are known to be true. So, and I have got a new theorem that I want to prove, or a new rider, new problem that I want to prove. So, I have got a set of sentences which are known to be true. All right. Now, given that the decision making takes this new proposition and asks this question, is it true? And the decision making machine will come up with the answer yes or no. Therefore, it will be yes, the answer will be yes if this new proposition is logically entailed by this set of sentences which are known to be true under a particular interpretation. That is what our proof mechanism is, it is nothing other than that. Okay. So, if we have got a set of sentences which are known to be true, and if a new proposition logically follows from that, then the decision machine will be able to say that yes, this is true. That is how our basic inference mechanism goes on. Now, we have seen modus ponens to be a very interesting and powerful way of inferencing. That is an inference rule. Now, we will look at another interesting inference rule, inference mechanism, that is known as resolution. But before going to resolution, quickly we need to have a look at a special form of representation of propositions, and that is called a clause. A clause is a special form. Now, before that, before defining a clause, we must know what is a literal. A single proposition, which we often call an atom. A single proposition is often called an atom, but a literal can be a single proposition or its negation. For example, P or not P. P is a literal, not P is a literal. Okay. Now, what is a clause? A clause is a disjunction, of all these literals. Now, what does disjunction mean? Disjunction means connection through or, not and. When we connect it with and, we call it conjunction, but disjunction means that all these literals are connected with or. So, you say P or Q or not R, this is a valid clause. Okay. Now, this is a particular form that is very useful for inferencing. Now, given any particular proposition, can we convert it to the clausal form? The form, the representative form in the form of clause is called a clausal form. So, how can we convert a compound proposition to a clausal form? There are some steps that we can follow and do that. Consider the sentence or the well formed formula A implies B or C implies A. This is not in clausal form because we have got literals, no doubt, but we have got disjunction, but we have got operators which are not disjunction. In a clause, there will be only disjunction operator. This is a particular form of clause that I am talking of, that is called disjunctive normal form, DNF. Okay? That is of interest to us right now. Okay, so how can I convert this to a disjunctive normal form? First of all, I can eliminate these implication signs by the simple rule that we know that if P implies Q, um, if we write P P implies Q, then that thing can be written as not P or Q, that we have already discussed. It can be written as not P or Q. So, in the same way, we can convert it in the clausal form. So, you see any implication can be converted to this. So, it was it is not probably visible, not of my clause was not of A implies B or C implies A. So, first I am trying to eliminate the implication sign. So, there was a not here, fine, let it be there. A implies B will become not A or B, and C implies A will become not C or A. This is the first step. Now, we have got this, still it is not a clausal form. Now, how can we make it a clausal form? We will have to eliminate the double negation sign and reduce the scope of the not signs using De Morgan's law. So, I had not of not A or B. So, I will remove this double negation. So, not, if I apply De Morgan's law, not applied over here will negate this. So, this will become A and this will become not B, but this operator will become AND, the dual of that, and similarly for this it will be not C or A. But unfortunately, as we have done this, I have got an AND operator which is not allowed in a clausal form. So, I have to do something more. The third step is, so what we got here is, you see it is not a disjunctive normal form, there are some ANDs also here. So, as we go down, we will have to convert it to this conjunctive normal form to disjunctive. So, I will first convert that to conjunctive normal form using these rules. So, I have got these rules, all right. So, by using the distributive and associative rules, A and B or not C or A can be converted to A or not C or A and not B or not C or A. This can further be reduced to A or not C, this is one, and not B or not C or A. Now, each of them you see is a disjunction, but they are connected with an AND operation. So, this is also called as, since they are connected with an AND, this is called conjunctive normal form. But our objective was to derive clauses, and in the clauses there were only disjunctions allowed. So, what do? We have got here individual clauses, they are satisfying the definition of clause, but they are connected with an AND. The answer is very simple. Each of these clauses can be looked upon as separate clauses which are true. So, we have to get the set of clauses. A or not C is one clause, not B or not C or A is another clause. So, thereby we derived the conjunctive normal form, but the conjunctive normal form consists of a conjunction of individual parts which are themselves in disjunctive normal form. So, they are clauses. So, we have got two clauses over here. So, in this way we can convert any particular proposition into the clausal form. Now, why do we look at all these? Why were we so much interested into getting the clausal form? Because the clausal form will allow us to apply a very interesting inference mechanism that is called resolution. Now, resolution is another technique of inference that we will learn. At the very beginning in the objective, we had said that we will learn to prove new facts given a set of facts. Now, proving a fact given a set of facts means logical entailment, proving the logical entailment, which we have also defined. Modus ponens was one way, but resolution is another way. Resolution is a sound inferencing mechanism, all right. Now, suppose X is a literal and S1 and S2 are two sets of propositional sentences represented in clausal form. S1 and S2 are two sets of propositional sentences that are represented in clausal form. Then if we have say X or S1 and not X, this and is a logical and not X or S2, then we can get S1 or S2. This is the basic principle that you can easily prove, that X or S1 and not X or S2. If we apply the associativity over here, then again we will have false or S1 or S2. Okay. So, then we get S1 or S2. So, that therefore, we can eliminate a literal with its complement. Therefore, we can here S1 and or S2 is the result of the resolution. So, this process is called the resolution. Okay. So, we take two clauses and resolve one literal with its negation, and the remaining part when combined gives us the resolvent. So, S1 or S2 is the resolvent and X is the element literal that is resolved upon, and the entire process is resolution. Now, what is the purpose of this? Let us take an example. If a triangle is equilateral, then it is isosceles. Okay? If a triangle is equilateral, then it is isosceles. That is told to you. It is a rule, a geometric theorem, which somebody had already proved. And again, if a triangle is isosceles, then two sides AB and AC are equal. That is a definition. If AB and AC are equal, then the base angles, the angles B and C are equal. That is something we know. Okay. ABC is an equilateral triangle, and suppose you are asked to prove angle B is equal to angle C. Can you prove it? Okay. Or we can try to do these things in this way, or suppose I change this a little bit. I want to, if now it is told ABC is an equilateral triangle, and I have been told to prove that these two angles are equal, B and C are equal, how can I prove it? My task is to prove angle B is equal to angle C. How do you prove it? There are different ways of proving. You can try modus ponens, or let us try with resolution, because we are learning it for the first time now. So, the first thing that we will be doing is convert each of these English like sentences into the propositional form. So, if a triangle is equilateral, then it is isosceles. I can write as equilateral ABC implies isosceles ABC. If a triangle is isosceles, then two sides AB and AC are equal. I can write that isosceles ABC implies equal AB and AC. If AB and AC are equal, then angle B and angle C are equal. This statement I can also say equal AB AC implies equal BC. And the last one was a statement. So, these were some if then type of implications or rules, and there is a statement ABC is an equilateral triangle. That statement, proposition corresponding to that is simple, equilateral ABC. Now, so from these statements we have got a set of propositions. Now, we have to convert each of these propositions into their clausal form. So, equilateral ABC implies isosceles ABC, that is turning out to be not equilateral ABC or isosceles ABC. Isosceles ABC implies equal ABC, that will equivalent be not isosceles ABC or equal ABSC. Equal ABSC implies equal BC, that will be converted to not equal ABSC. You see, P implies Q is not P or Q. I am sorry, I have made a mistake here again. It should be not equal ABSC or not equal ABSC or equal BC. Okay. So, here you see here this implication sign should be changed with an or. And the fourth one was originally in the clausal form. So, I need not do anything. So, I have got 4 clauses that were given, but I had another thing to prove. Angle B is equal to angle C. So, that when represented in the proposition is equal B C, and so equal B C is a proposition and is in the clausal form itself. So, I need not convert it to clausal form any further. Now, one approach that all of you must have done in the course of mathematics sometimes, that is called proof by refutation. Sometimes it is also called reductio absurdum. So, in order to prove equal B C, what we can do, we can also disprove not equal B C, that if we can prove that not equal B C is false, that implies equal B C is true. So, resolution actually tries to prove in that way. So, we were supposed to prove equal B C, and what I will be doing here is I will take the negation of this. So, not equal B C, and I will try to disprove it. That means, I will try to prove that not equal B C is not a logical entailment of the set of propositions that have been given to me. Okay? That is the method of resolution. So, let us try in this way. Here I have enumerated all the clauses that I had, not equilateral ABC, etc. All the clauses, including that ABC is an equilateral triangle, except the clause that I want to prove, or actually the clause that I want to refute. So, I take it on this side, not equal BC, not equal BC, that is the thing I want to disprove by resolution. Now, I will start the method of resolution. How can I do it? I will select one of the clauses from here, where I have to be a little intelligent and find out that okay, here is a clause which has got the complement of this literal not equal BC, and here is equal BC. So, I will select this clause. So, I will take this clause and I will try to resolve between these two clauses. Why did I select this clause? Because this had the negation of some part of the clause that I am going to disprove. So, when I select these two clauses, I resolve them, and when I resolve them, what I get is these two will resolve out, and the resolvent will be not equal ABAC, right. Now, when I get not equal ABAC, again I look over here and I will try to find out another clause which has got the complement of that. So, equal ABAC is here. So, I take that this clause and try to resolve between these two. As I resolve, what do I get? As I resolve, these two will resolve out. So, I will get not isosceles ABC. So, if you just have a careful look, you will see not this clause was actually meaning isosceles ABC implies equal ABAC. So, from that what have I got is, if it is equal ABAC, then I get isosceles ABC. All right. So, you just form it in the clausal form. So, I have got the not isosceles ABC. All right. Now, again the next step, I start with this not isosceles ABC and I will try to resolve. So, which clause has got isosceles ABC? This clause has got that. So, I select this clause. So, this clause comes in. I resolve between this resolvent and this. What shall I get? I will get not equilateral ABC. Now, I get not equilateral ABC and try to resolve further. Here there is an equilateral ABC. So, what will happen if I resolve between these two? One is stating it is equilateral ABC, another is saying not equilateral ABC. So, when I resolve them, I will get a null clause. And let us stop for a second and think of what is the significance of this null clause. The significance of this null clause is that I have arrived at a contradictory situation, a situation that is not supported by the given set of facts. There were a given set of facts like this, and I started with a premise not equal BC. And from there, by resolving, I have come to a situation where I have got a null clause, and the null clause essentially means that here is a contradiction. So, the premise with which I started is false. And what was my premise? My premise was negation of the goal to be proved, and that is disproved. That means the goal is proved. This is the method of resolution. Okay. So, the basic procedure for resolution, if we enumerate now, will be like this, that convert a given proposition into clausal form, convert the negation of the sentence to be proved into clausal form. So, first take the sentence to be proved, take its negation, then take it to the clausal form, and combine all these clauses together into a set and iteratively apply resolution to the set as we are doing and adding the resolvent to the set. So, if we go up a couple of slides earlier, say we are here. So, we tried to resolve this, and once we resolved this, we got this. Now, my resolution is taking place between this clause and all these set of clauses, this entire set, and we are resolving between this element and this element and getting a null clause. Okay. So, the fourth step is iteratively apply resolution to the set and add the resolvent to the set, and we will continue until no further resolvents can be obtained or a null clause is obtained. Okay. So, that is the complete step of resolution. Now, with that, let us quickly come to some practice quiz, which you will have to try. Please take down. Consider the following sentences. Mammals drink milk. Okay. Assume whether in the real world it is true or not, let us not bother about that. We are thinking of logical world. So, when we are making a statement, I am assuming that this statement is true. Mammals drink milk, man is mortal, man is a mammal, Tom is a man. So, these are 4 statements that we have said, all right. Prove that Tom drinks milk. Prove that Tom is mortal. This is very simple. Okay. Actually, you can also imply, you can also had put in some implications. Okay, it's fine. You can add in more implications, but what you can try to do is here represent all these sentences in the clausal form. Okay. Represent all the sentences in the clausal form. Now, prove 5 and 6. So, these are the two. Prove these two statements 5 and 6 using modus ponens. Sorry, all the typos here. And again try to prove 5 and 6 using resolution. Okay. Try to prove them using modus ponens and resolution. So, that is the assignment that you should try. So, quickly summarizing what we wanted to do today was, if we go back to the objectives, we have the objective of today's lecture was to show you what is the formal way of inferencing using propositional logic, and we have discussed about a couple of things. One is the truth table method. Using the truth table method, we can find out the truthness the truth of any compound proposition when we know the truth values of the individual propositions. Truth table is one method. We have also seen that there are some inference rules which are not dependent on any interpretation. The clauses or the propositions will evaluate to true or false based on some interpretation. So, we have got a set of propositions, we will give it an interpretation, we will have some to be true, some to be false under that interpretation. But the inference rule is independent, it is true for all interpretations. Modus ponens is one such inference rule. Okay. We have also seen a couple of inference rules like P or Q implies P, that is also another inference rule. But modus ponens, that is if P is true then Q is true, and we also know that P is true, then we can derive that Q is true, is a very powerful method of inferencing. This is typically a deductive method of inferencing. The other rule and a very powerful technique that we have learned today is that of resolution. Now, resolution requires that the propositions be converted into clausal form. Now, we have also seen the technique of how we can convert a proposition into its clausal form. The steps are that first we will have to do away with the implication sign, which you can easily do by converting P implies Q to the technique not P or Q, and after that we will eliminate the double negation, then we will apply the distributive and associative properties, and after that we will get a conjunctive normal form. Now, we will decompose this conjunctive normal form into each of those components which are themselves disjuncts. So, each of them will be clauses. We start with the set of clauses. Next, when we want to do resolution, we take the negation of the goal and convert it to the clausal form, and then we take all these known things as well as the goal to be proved and resolve it in the manner that has been described, iteratively apply that until we come to a null clause. If we get a null clause, then certainly the negation of the goal has been disproved and therefore, the goal has been proved. So, that much for today. You work with the quizzes that have been given. In the next lecture, we will see some of the limitations of propositional logic, and we will see how new languages have been developed to overcome those limitations.